Hello everyone, my name is Andrew Jones and I'm one of the LAs for Computer Engineering 331 at Penn State. This is the Notes, Hints, and Tips video for Lab 3. Now Lab 3 is considerably more difficult than Labs 1 and 2, and the best advice I can give all of you is to start as early as possible. Lab 4, Lab 5, and the final project all build off of this lab, so any mistakes that you make in this lab you'll need to correct for the future labs and the final project. These labs are not something that you can just do in an hour or two. It is going to take you a considerable amount of time to understand and implement them. If you do not start the labs early, you are going to have a bad time. So do yourself a favor and get started on this lab as early as you can. I want to give a brief overview of what we're going to be doing in the rest of this course regarding the labs and the final project. Labs 3 through 5, along with the final project, consists of implementing different stages and features of our 5-stage MIPS pipeline. The main structure of the 5 stages will be implemented through the labs, and the final polish and functionality will be implemented in the final project. There is also a bonus for the final project that implements additional instructions. Lab 3 is where we're going to do stages 1 and 2, which is instruction fetch and instruction decode. Lab 4 is where we'll do stages 3 and 4, which is the execution and memory access stages. Lab 5 is where we'll do the 5th and final stage, which is the write-back stage. In the final project, we'll implement forwarding behavior into our CPU, and for the bonus, we'll add control transfer instructions, which are your branch and your jump instructions. The bonus on the final project is extra credit, and I highly recommend that all of you try the bonus if you have time. Like I said on the previous slide, we're going to be implementing the first 2 stages of our 5-stage MIPS pipeline processor, specifically the instruction fetch and instruction decode stages. In the instruction fetch stage, we need to retrieve the instruction from program memory, increment the program counter by 4, and put the retrieved instruction into the IFID pipeline register. In the instruction decode stage, we need to direct the opcode and function code from our instruction to the control unit, which will determine the control signals for future stages of the pipeline as well as for the RegRT multiplexer. We also need to direct the RD and RT from our instruction to the RegRT multiplexer, which determines whether to use RD or RT for the destination register. We also direct the RS and RT from our instruction to the register file, or reg file, which accesses the values of the registers at addresses RS and RT. We also need to direct the immediate from our instruction to our immediate extender, which will sign extend the immediate from 16 bits to 32 bits. We then need to store pretty much all of these values except for RegRT into the IDEXE pipeline register. Here is the diagram for Lab 3. I'm going to go into greater detail about these modules and their functionality over the next couple of slides, as well as recommendations on how to implement them. The slides for this presentation will be made available on Canvas, so feel free to download these and use them as reference for the lab. The first module we're going to implement is our program counter. Our program counter will have 2 inputs, the clock and the next PC being 32 bits wide. The output of this module is going to be PC, which is also 32 bits wide. Initially, the output of PC should be set to 100 in an initial statement. This is 100 in decimal, by the way, not hex. The functionality of this module is that at the positive edge of the clock, the value of PC is going to be set to the value of next PC. Our next module is going to be our instruction memory. It's going to have an input of PC, which again is 32 bits wide, and the output is going to be instruction out, which is also 32 bits wide. Internally, the instruction memory is going to have a 2-dimensional register array, which we'll talk more about that on the next few slides. The functionality is that on any signal change, not just at any positive edge, but on any signal change, the instruction out is going to be set to the value of the memory array at the position of PC. I want to talk a little bit more about how we actually create our instruction memory in Verilog. Now normally in MIPS, memory is byte addressed, meaning that each address points to a single byte of data. However, to simplify for our implementation, we'll make our memory store whole words of data and only read and write on these 4-byte boundaries. This will simplify our instruction memory and, in Lab 4, our data memory. For our implementation, we'll need a minimum of 256 bytes, or 64 words. Since we'll only read from instruction memory on 4-byte boundaries, we can implement our memory as a 32 by 64 block, with 32-bit values and 64 different values to choose from. To create a 32 by 64 register array in Verilog, we do the following: reg 31 through 0, memory 0 through 63. This defines a 32 by 64 register array named memory. Note that while our memory is word addressed, our PC is still byte addressed. This means that we need to modify the input address in order to get the correct address in our memory. The process for this is actually quite simple. All we need to do is take the value of PC and remove the lowest 2 bits from it. We can access a word in memory stored at the value of our program counter in our Verilog implementation by doing the following. Instruction out equals memory at PC 31 through 2. This here removes the last 2 bits from the program counter. Remember that program counter is defined as 31 through 0. And then we use that to address our memory. We can also simplify this a little bit further. Since we only have 64 words in memory, we only need 6 bits to address all the values in data memory, as 2 to the power of 6 is 64. We can then write the Verilog as follows. Instruction out equals memory of program counter from 7 to 2. This here 7 to 2 is bits 7, 6, 5, 4, 3, and 2. That's our 6 bits to address all of the instruction memory. Note that this implementation will cause issues if we try to run a program longer than 64 words or 64 instructions, but we aren't going to ever do that in this course. Now, we'll also need to initialize some values into our instruction memory. To do this, we need to add an initial begin block to our instruction memory module and manually assign these values. Note that you'll want to remember that our memory is now word addressed, not byte addressed, so the instruction at PC 100 is now at word address 25. Be careful not to get these two confused. We can assign values to memory by doing the following in our initial block. Memory 25 equals 32-bit hex value, all zeros. This here sets the memory at location 25 to this 32-bit hex values, which in our case is all zeros. Note that our memory at this address should actually be a different value than 0. This is just an example to show you how we would initialize a value. You should use the 2 tables in parts 4 and 5 of the lab doc to help you find the values of the instructions. You can also use other formats of defining memory as well if you desire. I recommend that you do which you prefer or think is the easiest. I personally prefer this one here. Note that you only need to initialize the values of memory where instructions are located. For Lab 3, this will be words 25 and 26. You do not need to zero fill the rest of the memory. You can leave it uninitialized, which defaults to don't cares in the simulation. Our next module is our program counter adder, or our PC adder. It'll take the inputs of the program counter, which is 32 bits wide, and then a 32-bit hardwired value of 4. Note that this hardwired 4 can be implemented internally and not exposed as an input if you find this easier to do. The output of this module is going to be the next PC, which is 32 bits wide. The functionality will be that on any signal change, the next PC is going to be set to the value of PC plus this hardwired 4 value. Our next module is the IFID pipeline register. It'll take the inputs of the clock and instruction out, which instruction out is 32 bits wide. The output of this module will be D instruction out, which is also 32 bits wide. D in D instruction out stands for decode stage, which is the stage that it's being fed into. The functionality of this module is that on the positive edge of the clock, the value of D instruction out is set to instruction out. Our next module is the control unit. The control unit will take the inputs of the opcode from the instruction and the function code from the instruction. Both of these are 6 bits wide. Opcode corresponds to bits 31 through 26 of D instruction out, and function code corresponds to bits 5 through 0 of D instruction out, although this should be a review for you. The outputs of this module are the following: WREG, M2Reg, WMEM, ALUC, ALU-IMM, and RegRT. All of these, except for ALUC, are 1 bit wide. ALUC is 4 bits wide. The functionality of this module is that on any signal change, all of the outputs are assigned based on the values of the operation code and the function code, which I'll talk about a bit more on the next few slides. Now, the control unit in our CPU is the main controller for several other modules in our implementation. The outputs of the control unit specifically indicate the following. WREG stands for write register. When 1, this bit indicates that we are going to be writing to one of the 32 general purpose registers in our reg file. If we're not writing to the reg file, then this bit must be 0. M2Reg stands for memory to register. When 1, this bit indicates that we are loading a value from memory into one of the registers in our reg file. This bit is 0 on any other operation where WREG is 1. If WREG is 0, then the value of M2Reg is irrelevant and can be represented as a don't care value. WMEM stands for write memory. When this is 1, this bit indicates that we are going to be writing to our data memory, which we'll implement that module in Lab 4. If we're not going to be writing to our data memory, then this bit must be 0. ALUC stands for ALU control. This array of 4 bits indicates the operation that we intend to execute on the ALU, the module for which we will implement in Lab 4 as well. For now, the only operation that we are going to implement for the ALU is add, which should be given a value of 2 for the ALUC on our implementation. ALU-IMM stands for ALU immediate. When 1, this bit indicates that we want to use the value of the sign extended immediate rather than the value of QB for our ALU input. If we do want to use the value of QB in our operation, then ALU immediate should be 0. RegRT stands for register RT. When 1, this bit indicates that when we are writing to our register file, we want to write to the address in RT rather than the address in RD. If we do want to write to the address in RD, then regRT should be 0. regRT can be a don't care in any case where wreg is 0. Now, different instructions will require different control signals depending on what the instruction is doing. Chapter 4.4 of the Computer Organization and Design textbook has a bunch of tables that will help you figure out these signals. The easiest way to implement setting these control signals in Verilog is through case statements. For our control unit, we'll have a main case statement in our always block that uses the value of the opcode as the input. We'll also have another case statement inside of our main one for R-type instructions, as R-type instructions all use the same opcode, and their operations are then determined by the function code. This embedded case statement will use func as the input. A general layout of what the always block will look like is shown here. Note that the only instructions you need to implement for the lab are load word and add. Subtract is shown here to represent how R format instructions should be handled, as you will need to implement more of them in the final project, but you don't need to implement subtract for the labs, just the add instruction and the load word instruction. Our next module will be our regRT multiplexer. The inputs of this will be RT, RD, and regRT, with RT and RD being 5 bits wide and the regRT being 1 bit wide. The output of this module will be your dest_reg, which is 5 bits wide. The functionality is that of a multiplexer. On any signal change, if regRT is 0, then the destination register is set to the value of RD. If regRT is 1, then the destination register is set to the value of RT. Next, we have our register file. The inputs for our register file will be the values of RS and RT, both of which are 5 bits wide. The outputs will be QA and QB, both of which will be 32 bits wide. Internally, we'll have our 32 general purpose registers, each register being 32 bits wide, implemented as a 2D register array. This will be done similarly to how we implemented our instruction memory, but there are some differences that I'll cover in the next slide. The functionality of this module will be that on any signal change, the value of QA is set to the value of the register at address RS, and QB is set to the value of the register at address RT. Note that there are some additional inputs related to writing to the registers, but you do not need to implement these inputs and the related functionality until Lab 5, so don't worry about them for right now. Your register file will look similar to, but not exactly like your instruction memory. Declaring the registers will be similar to declaring our memory in our instruction memory, but instead of 64 words, we'll only have 32 words. So it'll be a 32 by 32 memory block. I also recommend that you name it registers instead of memory. In addition, our register file will be able to read from 2 locations at once. QA is set to the read from RS, and QB is set to the read from RT. Also, unlike our instruction memory, where we have to cut off the last 2 bits of our program counter in order to get the correct address, we can just pass in RS and RT to get the correct address, with no need to select certain parts of it in order to get the correct address. Obtaining the value of QA can be done in Verilog by the following code. QA is set to registers at address RS. Obtaining the value of QB is a similar process. Our next module will be our immediate extender. This will take an input of the 16-bit immediate from our instruction, and it'll output a 32-bit immediate, IMM32. The functionality of this module will be that on any signal change, IMM32 is set to the sign extended value of IMM. Note that sign extension is not 0 extension. Hardwiring 16 0 bits before IMM to get IMM32 is incorrect. Slide 60 of the Review in Verilog 1 PowerPoint will help you with implementing your immediate extender. Our next module is our IDEXE pipeline register. This here is very similar to our IFID register, but instead of having just one input and one output, we have a bunch of inputs and a bunch of outputs. I'll let you read through these on your own, but the functionality is pretty much the same. On the positive edge of the clock, the outputs on the right side of the module are set to the inputs on the left side of the module. Our final design module for our Lab 3 will be our data path module. This data path will take the input of the clock, and it'll have the outputs of the program counter and all of the outputs from the IFID and the IDEXE pipeline registers. Note that all of the outputs in the data path will be wires instead of registers. This is because all of their values are driven by the modules that they are connected to, as the modules handle setting the values at the proper times when they need to be set. Internally, your data path should instantiate an instance of all of the modules that we've previously described, as well as use wires to connect all of them together. The data path module will not have an always block. It simply is containing all the modules and connecting them together with the wires, as well as exposing parts of it for the test bench, which we'll talk about now. The final module for our Lab 3 will be our test bench. The test bench will have no inputs or outputs. The test bench simply serves to generate a clock signal for the data path and to read all of the signals coming in from the pipeline registers and the program counter. You'll have a clock register and the wires listed on the left here in your test bench to connect to the data path. You must name the wires these names or something at least relatively similar. If the graders cannot tell what your wires are meant to represent in your waveforms, you might lose points on your waveforms. Note that you should initially set your clock to 0, as initially setting it to 1 can cause some funky, undesired behavior during your simulation. Another important thing is that you do not want to merge your test bench and your data path into a single module. This will cause lots of errors with synthesis, viewing the schematic, and in the final project, your implementation. Remember that your test bench is not hardware, it is simply a tool to test the functionality of the hardware you designed. Your data path should be the top level module in your labs and your final project, both in Vivado and Quartus. If you're using Vivado, your test bench should be a simulation source and every other file should be a design source. If you're using Quartus Model Sim, then you'll need to compile both the datapath.vo file and all of your Verilog code files, including your test bench. This should be a review from Lab 1, but I want to put it out there just in case. Now, a considerable amount, if not most of your time on this lab will be debugging your code. It is very unlikely that your code will work on the first attempt, so I want to give you some tips on how to debug your code efficiently. Most of your debugging will most likely be related to incorrect waveforms. One of the best tips I have for debugging waveforms is to follow the data. By this, I mean looking at whatever isn't working in your waveforms and tracing where that data came from in your code until you find the error. This is perhaps one of the fastest and most efficient methods of locating problems in your code. Now, follow the data is best used for when your Verilog code is compiling, but the resulting waveforms are incorrect. The general process for this is that you start at the output signal that's incorrect, and you slowly work backwards through all the data path modules until you find the issue. There's 3 main tools that you can use: your waveforms, your code, and if you're using Vivado, RTL analysis. I want to show you all real quick how to view waveforms beyond what your test bench shows. In here, in Vivado, you can right-click a module here and click Add to Wave Window, which will add all of the signals of that module into your waveform window here. If you only want to add a couple of signals from a module, then you can left-click on a module here, then in your objects window here, right-click the signals that you want to add, click on Add to Wave Window, and they'll pop up right here. Note that once you've added your waveforms, in order to generate the actual signals for them, you'll need to click this Restart button up here. This process is fairly similar in Model Sim. What you want to do here is right-click a module here and click Add to Wave Window if you want to add all of those signals from a module. And if you only want to add some of the signals, you left-click a module here, and then in here, on the Objects window, you right-click a signal and click Add to Wave Window in order to view them in the wave window. You'll also need to use this button to restart your waveforms. I want to give a brief example of what following the data looks like. Now, one common error that can be made while writing Verilog code is having a misconnected or unconnected wire or register. This usually is due to typos. Unconnected wires in Verilog are usually set to high impedance states, represented as Z's in the waveforms. You can see that here with this signal. In this example, E destination register is outputting a high impedance signal after the first instruction enters the ID stage here at 15 nanoseconds. If you have an error like this, the first thing you'll want to do is look at the data path diagram and see what is connected up to the output. If we look at our data path, the first thing hooked up to our E destination register is our IDEXE register. You'll want to look through this module's internal logic and connections, as well as connections on the data path module. If you find that everything is connected and all of your logic is correct, then you can move on to the next module. In this case, nothing is wrong with the IDEXE register or its connections, so we'll move on to the next module. Our next module is our RegRT multiplexer here. Here, we do the same thing. Check the module's internal logic connections and the connections on the data path module, as well as the module's actual internal logic, making sure that's correct too. In this case, we find that our input wire RT here was named RG by mistake. This is a common error that many students have when they're writing the Verilog code, although usually it's not an example where instead of RT they type RG. Usually it's something along the lines of they swapped around a character in ALU immediate, so instead of ALU IMM, here they have ALI UMM, and then those differ from places to places in their code, and then that causes high impedance states. One really useful tool that's present in Vivado that I highly recommend you utilize is RTL analysis. On the Flow Navigator, which is the leftmost pane in Vivado, under RTL analysis, you can click Open Elaborated Design. to open an elaboration of your Verilog code. Then, under RTL analysis, you can click Schematic to see a schematic of all of your modules. We'll look at that schematic in a moment, but one thing I do want to note is that you do not want to use this schematic for your lab report. You want to use the one generated by synthesis. You will lose points if you use the RTL analysis schematic instead of the synthesis schematic on your lab report. If you want to include both schematics on your lab report, that's completely fine, but make sure that you at least have the one generated by synthesis. Now this here is our RTL analysis schematic. You can see here that on our RegRT mux, our value of RT is connected directly to ground. This isn't exactly what we saw happening in the simulation, but it's pretty obvious that RT shouldn't be hooked up to ground here. It should be like RD here, where it's hooked up to the instruction out wire here. The RTL schematic provides a very simple way to quickly analyze your data path and look for errors, and I highly recommend that you utilize it in debugging if you have access to Vivado. You can also click on each of the wires in the schematic to highlight their connections, as well as click on the plus icon on modules to show their internal circuitry. If you have time, I recommend you explore around more with the schematic view, as while Vivado might be a bit clunky, it does provide lots of useful tools to help to make developing hardware easier. Now before I end this video, I want to give you guys a couple tips that I have for this lab. None of these are requirements regarding how you complete the assignment, they are simply tips that I believe will keep you more organized, allowing you to more efficiently and quickly complete the lab. First, I highly recommend that you put different modules into different files. I understand that on the LabDoc tips, it says that you should put all the non-simulation modules into a single file, but I found that students who do use different files for modules spend less time debugging and have an easier time finding modules when they need to. Accessing the modules might require an extra menu if you have them in different files, but from my experience, it's much faster than scrolling up and down all of your code looking for the correct module. My second tip is that you should format your code. Proper indentation, formatting, and commenting of your code will make your life much easier when you enter the debugging stage of the lab. Students who don't format and comment their code tend to spend a lot more time debugging than students who do format and comment their code. How you format and comment your code is completely up to you. You do what works best for you. But remember that you will have to look back at the code you write while debugging, not to mention in the future labs and the final project, so make sure that it's easy for you to read and understand what's going on in your code. My third tip is that you give everything names that make sense. This kind of fits in with the format your code section, but I wanted to make a separate section for this anyways. The names of your modules, wires, and registers should make it very clear what they are used for or what they are trying to represent. If you name registers Reg1, Reg2, etc., this is quite ambiguous and will make your debugging very difficult. How you name your modules is completely up to you, with the exception of the test bench, but I highly recommend that you use the names provided within the diagrams. One thing I also recommend is that you define module names with their intended stage of the pipeline as a prefix. For example, I would define the program counter module as if_program counter and the RegRT multiplexer as id_RegRT mux. IF and ID are corresponding to the stage of the pipeline that those modules are in. Again, how you name everything is up to you. You do what works best for you. I know that I put this tip at the beginning of this video, but I cannot stress how important it is to start early and to give yourself enough time to complete the lab. I recommend that at minimum you start a week in advance of the due date. This will give you plenty of time to write your code, debug it, and if you need to, access office hours. If you can start earlier than this date, then I highly recommend that you do so. And if you think you can start later than a week in advance, well, good luck, I wish you the best. My fifth and final tip for you is that you should utilize office hours. The office hours of the TAs and LAs are provided on the syllabus, and the TAs and LAs will gladly help with all aspects of the lab. Note that before asking your TAs and LAs to debug the code, please try and do some debugging yourself. Remember to follow the data. If you can't access office hours for whatever reason, you can still email TAs and LAs through either Canvas or through their PSU email, and they will help you through there. The TA and LA emails are also provided on the syllabus, and if you do email them, please provide lots of detail about exactly what's causing you trouble in the lab. Screenshots and Verilog code files help greatly with this. This concludes the video for Lab 3. Again, if you find you have trouble in the lab, do come to office hours or send any of the TAs or LAs an email. Have a great day, and remember, follow the data.